This is AP Calculus AB, and in this video I'm going to talk about section 7.2, anti-differentiation by substitution. So really I typically refer to this as integration by substitution. But when we go through this section, you'll notice that we're going a little bit out of order in the textbook. And so what we're trying to do is kind of pick up where we left off with integration. So if you remember back in chapter 6, our last unit, that's really what we were focused on, was integration. And so what we want to do here is just kind of finish out all of our integration techniques. And then we're going to make a little bit of a shift in this unit and start talking about differential equations, which will involve integration, but it's a little bit of a change of topic. So we'll do this integration by substitution first, and then we'll circle back to section 7.1 and pick up the ideas about differential equations. Okay, now one thing you are going to see with that said, we are going to see some questions in this section. Since we're going a little bit out of order, you're going to see some questions that might look different than what you're expecting. So notice this question. It says solve dy dx equals x squared minus sine x is equivalent to evaluate the integral of x squared minus sine x dx. So we're going to talk about why that's the case when we get to section 7.1. But for now, just understand that when they ask you to solve those differential equations, we're basically just solving an indefinite integral, and then eventually we'll look at definite integrals as well in this section. Okay, so when we go through and do integration by substitution, keep in mind that we have a lot of derivative rules that we haven't really been using to do antiderivatives yet. So things like e to the u, we haven't really been taking antiderivatives involving like e to the x or e to the u, or natural log of u. That's one we're not really going to see very often, but there is an antiderivative rule for the natural log of u. The one that you might see once in a while, remember we have the derivative rule for if we take the derivative of a to the u power, so an exponential expression with base a, then we're going to get a to the u natural log of a. So we have an antiderivative rule for that as well. And then also we have an antiderivative rule for log of any base. So I put all four of these here, but really these are the two that we're probably going to see very often. These two over here, those are really rare occurrences where we would see an integral of a log function. And so those are not really rules that we typically memorize. So you don't really have to worry about those two, but just realize that there are rules when you take the antiderivatives of natural logs as well. Okay, so let's take a look at what we're going to do in this section. So the whole idea behind this is a lot of times when we're dealing with integration, we start integrating functions that are much more complicated than ones we've been looking at up until this point. So all of the stuff that we looked at in chapter 6, when we had to integrate, we were able to either just take the antiderivative in the form that it was in, we could find the integral by area, or we could do a little bit of algebraic manipulation, and then we could take the antiderivative. Well, there are a lot of integrals where those basic methods are not going to work. And so there are more advanced integration techniques that we can use. And the one that we cover in this class is called integration by substitution. Now, there are also other integration techniques that are a little more advanced. There's integration by parts. There's integration by partial fractions. There's something called trig substitution. So there's different things that we can do to solve integrals out. But in our class, the only other method we're going to talk about is integration by substitution. Okay, so I'm going to show you kind of what these things are going to look like and something to be careful about. Because what we're going to do is we're going to replace our expressions with a simplified function that will allow us to use our basic antiderivative rules. And when we do this, we typically use what we call a u-substitution. We plug in an expression for usually like x terms. we create a u that is some function of x. And then we rewrite that integral then in terms of x. So there's three integrals down here that I want you to take a look at. So the first one here, you can see this is what we've been doing, right? We have an integral in terms of x. We just take the antiderivative, very, very straightforward. Well, after we do our substitutions, sometimes we'll end up with an integral like the second one. So notice now we have a function in terms of u. So we take the antiderivative, and then remember, u is equal to x squared. So after we've taken the antiderivative, we do what's called back substitution, and then we end up with a result. Okay, so that's typically what our integrals are going to look like. What we don't want to do is what the third one shows. So the third one is showing, okay, we've got our function now written in terms of u. We've done our substitution. We rewrite our integral now in terms of u, and then do back substitution, and then do the antiderivative. So this last one is not really something we would do because you're back substituting before you've even taken the antiderivative. You're basically undoing your substitution before it's been any benefit to you. So usually these two are the two that we're going to be using. This is what we've been doing, the first one, and then the second one is what we're going to do in this section. So I know that's a little bit confusing right now, but once we've gone through a couple of examples, you'll see how those things make sense. Okay, so the main idea, what we're trying to do is we're trying to take integrals that are complicated and we're trying to rewrite them in a simplified form. So we usually start with some function of x that we're trying to integrate, and we replace it and rewrite it as a function in terms of u. Okay, so the process for this, once you understand how to do it, is fairly simple, but it might take you a little bit of time to kind of wrap your head around it. So I've got a worked out example here first, just so you can see what we're going to be doing. So we've got this integral x squared times the square root of 5 plus 2x cubed dx. And over here on the right, what's been done over here, this is usually the hardest part of the process. So we're going to have to come up with that part of it. What we have to figure out is what do we want to choose to be the u so that we can rewrite this integral in a simplified form. If you notice right now, I can't take the antiderivative of that, at least not very easily. It could be done if you really kind of think about chain rule stuff, but we really don't want to have to try to sort through all of that in our heads. So what we're trying to do is simplify this so the chain rule stuff is kind of taken care of. So I'm going to define my u to be 5 plus 2x cubed. And then if I were to find du dx, let me write that out here, du dx. Du dx would be equal to 6x squared, right? Well, if you multiply the dx over, that gives you du is equal to 6x squared dx. The reason we do that is because we want to be able to see what are we going to do with this integral to get everything in terms of u. Okay, now, notice in this integral, we don't have a 6x squared times dx. So we're going to have to make it have a 6x squared times dx. So anytime you have a missing constant value, we can make a constant value show up within an integral just using our properties that we talked about. We can move constants in and out of the integral if we have a constant multiplied to our function. So that's what's been done on this step. We multiplied the x squared by a 6. And now so that we don't change the value of the integral or the function, what we're going to do is we're going to account for that 6 by multiplying out here by 1/6. So 1/6 times 6 just gives me 1, and then I'd be back where I started. But I want it written in this form because now I'm going to replace everything in this integral. This square root of 5 plus 2x cubed becomes u, because this is my u to the 1/2, and then the 6x squared dx, remember that all becomes du. And so now I've got an integral that's written in a really simple form that is equivalent to the one that I started with, just written in terms of u. And now I can do my antiderivative just like we always would. We just use the power rule. Use the power rule, take the antiderivative. We'll have a solution here in terms of u. But remember, our original integral was in terms of x. So what we really want to do then is back substitute. Plug back in for the u, and we get our final solution here. So in the end, we have our antiderivative in terms of x, but we went through that u substitution to kind of work around all the chain rule stuff that was going on in there. Okay, so when you see it that way and you haven't really worked through them yet, sometimes it seems kind of confusing, but after you've worked through 3 or 4 of these, you start to see that this is pretty simple. So I'm going to show you one of these here, and I'm going to have you try some of these where it's kind of in a very, very easy setup. And the reason that these are easy is because the u's already been defined for you. And so you don't have to do a lot of thought. And I'll show you on the next type where the u's not defined that there's a little bit of foresight that you have to solve these out. You have to think ahead a couple of steps. But when the u's defined, we can skip that part of it. Okay, so we're trying to integrate sine 3x dx. Some of you might be able to do that in your head, but we're going to use the u substitution process. So this says let u equal 3x. That means my du would be 3 times dx. And remember, that's because du dx would be 3, and then I multiply the dx over. So for this integral that I had, I need to have a 3 dx in it. So what I'm going to do is I'm going to put a 3 inside here. And the reason I'm doing that is so I have a 3 times dx, right? So since I put a 3 on the inside, so that I don't change the integral, I have to put a 1/3 on the outside. So all I've really done, if you kind of think about it, is I've factored a 1/3 out of the integral. And like I said before, you can move constants in and out of the integral. It doesn't have any impact. Okay, so now that we've got that done, let's do our substitution. We still have this 1/3 here. And then when I integrate, my sine 3x becomes the sine of u, and the 3dx becomes du. And now I just have to do my antiderivative. The antiderivative of sine would be negative cosine. So I'm going to get negative 1/3 cosine u plus c, because it's an indefinite integral. And now just do your back substitution. Plug back in for the u, and we get negative 1/3 cosine 3x, and then plus c. Okay, so that's really the process that we're going to be using there. We're going to have to define a u, find the du, make sure that we can make the du appear within the integral, do the substitution, take the antiderivative, usually using a basic antiderivative rule at that point, and then do back substitution. Okay, so I'm going to show you one more of these, and then I'm going to have you try a few. This one's a little more complicated. This is one where you probably would want to use a substitution, even if you could do the last one without. So we have the integral of x cosine 2x squared dx. So notice the u has been defined here. U equals 2x squared. That means my du is 4x dx. Okay, so I need to make a 4 show up in here. So what I'm going to do is I'm going to rewrite this integral. I'm going to put a 4 inside, 4x cosine 2x squared dx. And then that means I need to put a 1/4 on the outside so that I don't change anything. Now, remember, the whole point of that was I need a 4x dx to show up because that's what I have as part of my substitution. Okay, so once that's been done, now I can go through and I can start solving this out. So I'm going to do my u substitution. This cosine 2x squared becomes the cosine of u, and then the 4x dx becomes du. Now I've taken what seemed kind of complicated and I've turned it into a really, really simple antiderivative here. So this will be 1/4 sine u plus c. And then in the end, I can do my back substitution, replace that u. This would be 1/4 sine of 2x squared plus c. Okay, so again, pretty simple once you kind of understand how the process works. And like I said before, this is kind of easy right now because the u is being chosen for you. Where these get a little more complicated is when you have to decide what the u is going to be. All right, so there are 3 more of these on this, or 2 more of these on this page, and 1 on the next page. So 3 total that I want you to try on your own. I want you to do these 2, and then do the first one on the next page. So you can pause the video, work those 3 out, and when you unpause the video, I'll show you the solutions to those. All right, so here's what you should have for those first 2. You can see that what I've done here, I needed a du this time of 7 dx. So there was a 28 inside the integral on this one. In order for a 7 to show up, we can just factor a 4 out of the integral. So once you factor the 4 out, replace everything in there. The du, 7 dx becomes du, and then the 7x minus 2 cubed just becomes u cubed. And again, now it's just basic power rule. And once you've done your antiderivative, don't forget that that 4 was out in the front. And just go and do your back substitution. So 4 times 1/4 will give me 1. So I really just have u to the 4th. And then when you substitute back in for the u, you have 7x minus 2 to the 4th plus c. Now, one thing I didn't mention before is that you can always verify your answers on these indefinite integrals, right? We could always take the derivative of this, and we should see that the derivative is 28 times 7x minus 2 cubed. And if you worked that out, you would see that that was the case. All right, next one, same kind of thing. You can see we have this square root in the denominator, and we have a 9r squared in the numerator. Well, the u here has been chosen for us. U is 1 minus r cubed. That means our du is negative 3r squared dr. So we don't have a negative 3r squared dr in the given expression, but we can factor a negative 3 out of the integral, and that'll leave us what we need to do our substitution. So what's in the denominator there, this part of it, the part down there, becomes this part right here, becomes u to the 1/2 in the denominator. So that's the same as u to the negative 1/2. So that's where that came from. And then the negative 3r squared dr becomes the du. And then from there, again, it's just power rule. So add 1 to the exponent, divide by the new exponent. So in the end, don't forget about the negative 3 out in front. I end up with negative 6 u to the 1/2 plus c, and then just back substitute in for that u. Okay, so again, fairly simple once you understand the process. And then here's the last one. This one was pretty simple. When you have the problems written out, which I know, I'm not handing you assignments on paper or quizzes on paper right now, but when you're doing this, for example, I don't know how the AP test is going to look at the end of the year, but let's say we do the AP test in person and you have to write it on the paper. You can save yourself a little bit of work in those situations if you don't rewrite the given problem. Instead of rewriting it, what I'm going to do is just make my u-substitution form show up on the given expression. So I have this integral of sine x e to the cosine x dx. They gave us u as cosine x. That means my du is negative sine x dx. So I need a negative inside the integral. You can see I wrote it in there. So I don't change anything. I put a negative on the outside because those two negatives multiplied together give me a positive, which is what I started with. So now when I do my substitution, it just becomes e to the u du, which is really, really simple because the antiderivative is just e to the u. And then when I back substitute, I get negative e to the cosine x plus c. Now, notice I skipped a step on that last one. Sometimes you're going to get to the point where you don't need to do all the intermediate steps. And that was what I was trying to show you here, is that when you get comfortable with it, you can start to skip some of these steps. I always want to see the integral rewritten in terms of u, but then what you do between that form and your final answer, what steps you can skip in there, that's going to be, it's going to vary person to person. Some people can do a lot of things in their head. Some people are going to need to write out every step. And whatever you're comfortable with, that's what you should show. And as you get more and more practice, you'll find that it becomes easier and easier to skip some of those steps. Okay, so what we have after that are integrals where the u is not given. And this is where u substitution becomes a little more complicated. So when we have these types of problems, we have to kind of think a couple of steps ahead to see if our substitution is going to work. So what I have to do is, and I don't want to just jump into the problem. It's kind of like when we talked about derivatives and we got to the point that we had chain rule, we started to have options on how we could take the derivative. So we didn't just jump into the question as soon and did the first, do the first thing that you think of. What you really want to do is consider different ways that you can set it up and kind of think, is that going to work? Is it going to create a big mess for me? That's kind of what you should be thinking about as you work through the process. So here I've got the integral of x times the square root of 1 minus x squared dx. So this one's kind of obvious. What I want to think about, and I would do this in my head, but what I want to think about in my head is, okay, let's say u was 1 minus x squared. If that's my u, what would my du be? So in my head, I would be thinking, okay, my du is negative 2x dx. And then I want to look at my integral and think, okay, can I make that happen? Can I get a negative 2x dx to show up? And in this case, yes, I can. So I know that substitution is going to work. So usually all of this that I have written right here, I do in my head first before I actually write it down. You do want to write it down every time because it shows what your process is, but you don't want to just start writing down before you've thought through it, because sometimes you have options on what to choose for the u, and you might choose the wrong u initially, and you don't want to start having to cross things out and erase and start over, because you can usually think through this pretty easily and figure out if it's going to work or not. Okay, so that means this integral can be rewritten. I'm going to need a negative 2 on the inside, so I'm going to rewrite this integral so that I can do my substitution. And now when I do my substitution, I've got negative 1/2 times the integral. This becomes u to the 1/2 du. And if I've done my substitution correctly, then I should be ending up with an integral that is now very, very easy to solve. A lot of times it'll be power rule or sometimes a really easy trig antiderivative rule, but it's usually going to be something very simple to work with. Okay, so at this point, I'm going to take my antiderivative. Don't forget about the negative 1/2. So for the u to the 1/2, we're going to get 2/3 u to the 3/2, and then plus c. And then I just need to do my back substitution. When I multiply these constants together, I'm going to get negative 1/3. U to the 3/2 is the same as 1 minus x squared to the 3/2, and then plus c. Okay, so again, fairly straightforward. Not anything that's too tricky. Once you've worked through a few of these, you'll start to see that it's pretty easy to solve these out once you've identified the correct substitution. Okay, so there are a bunch more of these here. 1, 2, 3, over here, 4, 5, 6, 7 more. So what I want you to do is I want you to pause the video and I want you to work through as many of these as you can. You might get a little bit stuck on some of these ones involving trig functions because there's a lot of options that you have to consider in those situations, but you should be able to work through the majority of these. So pause the video, work through as many as you can. When you unpause it, I'll show you the solutions. All right, so here's the next one. You can see that I've got 5x over 4 plus x squared, and you can see I chose my u to be 4 plus x squared and my du to be 2x dx. And when I did that, I got a very, very simple expression here. I essentially have u to the negative 2 du. Remember, we're not going to use a natural log. That's 1 over u squared. That's not a natural log. That's just a power rule question. So you do the power rule. You get essentially negative 1 over u for your antiderivative, and then from there do your back substitution. Okay, so the only time you're going to use a natural log is when you have something that's like a 1 over x to the first power type of situation, or a 1 over u to the first power. Okay, so the next one. This one is one where we do use a natural log. So we started out with just dx over 2x minus 3. So if I choose my u to be 2x minus 3, that means my du is 2 times dx. So when I do that substitution, you can see that I have du over u, or which is essentially 1 over u du. So you should recognize that as being the derivative of a natural log. Now, the thing you have to be careful about, it's not just natural log of u, it's natural log of the absolute value of u, because we have to consider the domain of the original function, right? We didn't have any domain restrictions given here. So it's possible that that u expression could turn out to be negative. So I have to account for that by using an absolute value. And so in the end, when I do my back substitution, I have 1/2 natural log of absolute value of 2x minus 3 plus c. All right, next one here. This is where these get kind of tough. We have cotangent 7x dx. So when you have these types of questions with trig functions, this is where that sort of thinking ahead really can start to pay some dividends. So obviously I can't do an antiderivative for cotangent, and you have to know your derivative rules for the trig functions really well to know that. There's no derivative rule that will give me cotangent as a result. So I have to think about, okay, what are my options here? Well, could I use a trig identity to rewrite this? Can I just, break this apart somehow? Well, cotangent's the same as cosine over sine. So I rewrote it as cosine 7x over sine 7x. And now it's in a form where I can actually do a substitution. So you might think that you have options here, but you really don't, because the dx is attached to the cosine. So I really need to choose my u as being the sine 7x and my du to be the 7 cosine 7x dx. And so I need a 7 in the numerator. So I put a 1/7 on the outside, so I didn't change anything about the integral. And when you do your substitution, we get du over u again. So just like the last one, we're going to get natural log of absolute value of u for that antiderivative. Don't forget about the constant out in front, and then do your back substitution. So you'll start to see that after you've solved 5 or 6 of these on your own, you're going to get faster and faster with this. And then eventually you'll get to the point where you can look at these and you'll be able to know within 10, 15 seconds, for the most part, you'll be able to know whether or not your substitution is going to work. But there will be times with these trig functions that you'll get stuck a little bit and you'll have to try a few things. So the next one's an example of that. So we had dx over cosine squared 2x. Okay, so you might think, okay, I'm going to make my u cosine 2x. But in order to do that, that means my du would be negative 2 sine 2x. Well, I don't have a sine in this integral, and I can't put one in there. The only thing we can move in and out of the integral are constant values. So we can't just have a sine 2x randomly show up there. We would be changing the function. So what we have to do is think about how can we manipulate this. You might think about a Pythagorean identity because it's a cosine squared. But the easiest thing to do is to just rewrite this as a secant squared. So once you recognize that it's a secant squared, this is actually really simple because I do know an antiderivative for secant squared. You may be even able to do this at this point without even doing a u substitution. But if you do the u substitution, your u would be 2x, your du is 2dx. And then from there, I can rewrite this as 1/2 integral secant squared u du. Antiderivative of secant squared is just tangent, and then do your back substitution. But a lot of you might see it here and go straight to that solution. And if you can skip the u substitution on these sometimes, that's totally fine. Really what it's supposed to be is a tool that aids you on the more complicated questions. Okay, so here's a pretty tough one. We've got cotangent squared. So with the cotangent squared, I've got a lot of things that I can think about here. And this one you might stop and think about for a while before you come up with a solution. And a lot of times with these, you're going to get stuck the first time you see a certain type of integral. But once you've worked one of them, the next time you see one that's like it, you'll have a little more experience and you'll have some ideas to draw on as opposed to just kind of sitting there and staring at it for a while. Okay, so for this one, for cotangent squared, the first thing you might think of is cosine squared over sine squared. If you mess around with u substitutions there, you're going to see that it doesn't work. So then I went to Pythagorean identities. Cotangent squared is the same as cosecant squared minus 1. Well, with that being the case, I know there is a derivative rule that has a result of a cosecant squared. So from there, I did a u substitution. And again, you may not even need a u substitution once you get to that point. But if you need the u substitution, what you do then is, I'm going to say my u is 3x, my du is 3dx, and then I just did my substitution, and you can see down here, I ended up with a cosecant squared minus 1, and my antiderivative of cosecant squared is negative cotangent, because the derivative of cotangent is negative cosecant squared. So I ended up with a negative there, then I have my minus u. Notice the 1/3 is multiplying to both of those terms, so you've got to be careful about that. And then do your back substitution, plug in your 3x, and then remember the 1/3 right there. That's why that's an x, because we had 3x times 1/3 gives me x. Okay, so that's probably the hardest type, is when you have that and you have to start thinking about trig identities. We won't do a ton of them like that, but you will see those from time to time where you've got to think about trig identities. Okay, so here's another one. This one's a little easier, but again, you need a trig identity. So we have a cosine cubed x dx. I can't take an antiderivative here. I can't do a u substitution in the form it's in, because my u would be cosine x, my du then would be negative sine x dx. I don't have a sine. I can't make that show up without doing something else. So then I have to start thinking about, how can I manipulate this? Well, cosine x, or cosine cubed x, is the same as cosine x times cosine squared x. So that's what I did, was I broke it apart, and then my cosine squared can be written as 1 minus sine squared. Then I can do a substitution, and you see how it works out from there. So I end up with just a 1 minus u squared, which is very simple. But again, when you first see these integrals involving trig functions, you might get stuck. Don't feel like you are totally lost if you're stuck on the ones with trig functions. Those are really, really hard ones. And they just take a lot of practice, and the more of them you do, the easier they become. All right, the last one here I have starred, because this is one that you will definitely see this form again. You'll see it on your quiz. You'll see it on your test. This is one that's always on the AP test. And what it is, it's a really obvious one once you've seen one of them. So it might not be obvious at the very beginning, but we do have a natural log of x here, and we do have a 1 over x here. So if I make my u natural log of x, my du is 1 over x dx. So I actually already have everything I need. So when I do my substitution, this is really just u cubed, and then do your power rule, and then just back substitute, and we have natural log of x to the 4th over 4 plus c. So take note of that one. That is one particular type that is definitely going to show up again, and it's, once you understand it, it's very, very simple, but it's so common from an AP testing perspective that I am definitely going to make sure that you know that particular integral, just because you don't need to be getting hung up on something simple like that. If we've practiced it, then you can save time for more difficult problems down the road. Okay, so when you're going through your homework assignment, right now I only want you to focus on indefinite integrals. Next time, we're going to talk about definite integrals. Now, keep in mind, most of these problems are not going to involve all this stuff with trig functions. I wanted to show you some of those here so that you could see how they work. For the most part, your homework problems are going to be more like these ones that we did at the beginning. So if you felt okay about those, you're going to be okay on the homework. You might get a little bit tripped up on the few trig integrals that we have, but we can talk about those. We can talk our way through those next time. If you get stuck on the homework, we'll go through those in class.